Okay, cool. So derivatives are kind of the thing that we have to master. We gotta know how to do derivatives for sure. Those are the easy problems that you guys have to do on your exams for sure. So let's kind of go over the rules of the derivatives so that we're kind of like all, on the same page about that, if that's all right with y'all. And feel free to ask questions. I mean, this is an exam session, so whenever you guys, feel like you have a question or something like that, feel free. It's just like any other session that we have. So let's get this thing underway. So I'm going to talk about derivatives. Here we go. Talk about derivatives. Talk about what is a derivative to start off. A derivative is a rate of change. So that's kind of the underlying theme of it. And then we have some like simple rules that we normally use to try to figure out, what that derivative is. So that first can start off, we can start off by talking about the power rule, which is kind of the power rule. Anybody know any other rules that we want to throw out there?
Quotient rule.
Quotient rule.
Product rule.
One last rule that's really
Chain rule.
Chain rule. All right, Devin, cool. All right. That's very important. So I want to highlight the chain rule because it's a little different from other rules. It's not like, doesn't have a specific formula other than, or a specific situation, I would say, other than that it's a derivative of a function within another function. So kind of the way that I like to describe it, if you've seen this before, cool, but so not everybody has, is if you had like a sandwich, and this is not like a restaurant or something like that, but you have a sandwich, you have some lettuce, and maybe you also have some, I don't know what you got like a sandwich. You might have had some. So the idea is you want to treat the outside function. You want to treat that outside function as like the bread of the sandwich. Okay. You take the derivative of the outside. So I guess we're going to call that outside prime. Okay. Times the derivative of the inside. That's going to be your chain. So we're going to try a couple of examples to try to, make sure that we have this, fully under wraps. Let me know if I need to stay on the same page. Zoom's kind of interesting because the professors kind of like sometimes go too fast and just everyone's still trying to figure out the right pace to go at. So feel free to let me know if I'm going too fast or you need me to stay at a certain page to kind of get this thing going. So let's try out a couple of examples. I'll give y'all like maybe a minute or two to do them. Feel free, of course, to DM me in the chat if we got somebody said something. Okay. I mean, all right. This lag is not cool. Y'all see y'all getting lag. All right. Yeah, that's weird. Okay. Audio keeps glitching, echoey. All right. We'll try to see. Can y'all? Has it been that way since the beginning, or is it kind of like just happening. Huh, okay. So I'm gonna write some calc problems, and while y'all are doing the calc problems, I'm gonna try to figure out this audio and video thing so it's a lot more smooth. That helps. So I'm gonna write some problems over here. So we want the derivatives just to kind of a warm up for these problems. So work on these. Let me make this thing more visible for y'all because I wrote through the problems. All right, so these are the problems in case, and this is from the practice. These two right here are from the practice exam. So try those out. While y'all trying that out, I'm gonna figure out this audio thing so it sounds better for y'all. Okay, this is an audio test. Does this audio sound better?
Yeah, sounds better.
All right, cool. Because I grabbed a microphone. So I've seen this thing right here. So I grabbed a microphone. So that was my backup because you can't trust technology. All right, so now that the audio is working, we can now we can keep this thing on rolling. So let's kind of let's kind of figure out some answers to this thing. How do I make this thing in the damn default color? I don't know, but that's my problem right now. Okay, what color should we pick for this? I'm feeling lime green, a little Tulane in there. All right, let's start off with the first problem. Anybody want to chime in on the answer to it?
Can you share your board?
What did you say it was?
Can you share your screen with us?
Oh yeah, sorry. Yeah, I need to share my screen. Thank you. Y'all want to see? Y'all want the answers? All right, cool. All right, let's. Here we go. This is the first one. So, sorry. What kind of rule are we gonna try to use here? What kind of rules do we see that we're gonna need to use? This is not a 5, by the way. This is like x to the -5. I'm just. Oh, I keep writing 5. All right. So just looking at it, you want to first look at a problem and figure out, okay, what rules am I going to need to use? Right? Because you want to make this thing kind of a habit. So anybody want to shout out what kind of rules they know they're going to have to use for this?
Chain rule.
So we got a power rule right here. Okay. What other rules are we going to have to use?
Chain rule.
Chain rule. Good, Zoe. Chain rule. Sorry, who may said that? Who said chain rule?
Me.
Zoe. Okay, cool. Good. So Zoe and Yume came in pretty clutch with this. So we got a power rule and then we got a chain rule. Okay. Nice. So because we have those things, we now kind of have an idea of, okay, this is what we need to piece this answer together. So let's do just that. So the first thing we're going to do is take the derivative of the outside first. So what's the outside portion of this function?
A -1/3.
Yes, ma'am. Abigail, nice. So this is the outside part. So that's why the parentheses is helpful, because you first got that outside exponent first. So if you take that derivative, you're going to move that exponent to the front. So you're going to have -1/3. Okay. -1/3 times 4x. So you do the outside function, then you keep that input the same. So everything else is going to stay the same, except the exponents and the outside and the part that you move to the front. So this is the derivative, in case we were not sure. Okay, that's the derivative. Let me kind of create some more space here.
Is it still going to be raised to the, is that -1/3?
It is -1/3, -1/3. Sorry, not -1/3. I'm sorry. It's going to be -4/3, right? -4/3, not -1/3. So we're changing that to a 4. Thank you, man. -1/3. So we subtract 3/3 because that's 1. Now you've got -1/3. Okay. So what's next?
Multiply it by the derivative of the inside.
Yes, ma'am. Okay. So what's the derivative of the inside?
I got 4 minus 5x to the -6.
Okay. So we got 4. Then we got -5x to -6. All right. That is your derivative. Any questions about that? All right.
Keep it moving. Okay, so the next problem we've got, I'm just gonna keep it
So
white
do we
for,
not have to simplify that?
excuse me?
I'm sorry. So do we not have to simplify that further?
I mean, if it's up to me, I say no, but this problem can't really be simplified.
Okay.
So, I mean, generally you probably would, but I think for a session like this, you know, really the priority is to make sure that your basic concepts are drilled down. You know, simplification is I mean, it is a simple concept because simplification is something they've always taught you how to do, or maybe not. I don't know what, you know, but I would say that for now, let's kind of focus on the basic thing. Okay, are your derivatives right? Is your thought process right? And then at the end, we can worry about simplification. And we're gonna see examples of simplification anyway. So, but for now, don't worry too much about that. Okay, so hopefully that answers your question. Let's kind of move to the next one. I think it was tan inverse. Tan inverse. They want the derivative when x is equal to 2. It came to my attention that the practice people actually said that it's actually tan inverse of x squared. That's okay. That gives you a chance to do both. Practice with both. Anyone know the derivative of tan inverse?
Secant x tan x.
So that's the derivative of, I believe it's derivative of secant x tangent x.
Isn't it 1/1 plus x squared?
Yeah. Thank you, Kat. So it's the derivative. It's 1/. This is not one of those derivatives that there's like a formula, an easy kind of like, oh well, this is how you derive it. Like the inverses are kind of fucked up. So you wanna have that. So if you can solve that one, then the practice one shouldn't be too bad. What's the difference between the one that you have in this magenta color versus the purple one you've got here? What's the big difference that you've got? What's going to change in your derivative?
You have to do a chain rule.
Got to do a chain rule. What's the answer to the chain rule?
2x.
Right, you're going to have a 2x2 as well. So you're going to be 2x over 1 plus 1 plus x squared. Just because you're going to be multiplying that 1/1 plus x squared times 2x because you got the chain rule with the x squared. Okay, any questions about that? Before we tackle kind of so you got two more problems from the practice just to kind of get these derivatives. I mean, I'm just going to say this. I know the exams are going to be different now because they're on Zoom. So you want to take full advantage of that. I mean, the university's got pass fail now in case you don't feel good about it. But I think it's still a good opportunity to spice up your grade. You've got your exam. You're basically taking it at home. And so there's not much there's less, I guess it's favorable for you in that way. So you really want to take advantage of that and know your derivatives. Really, derivatives are kind of the main key to all of this. So know your derivatives. It's the same thing I would say if we were still back at Tulane. Know your derivatives. It's important. Okay, let's get to this next stage. So we've got this x ln x e to the x plus e to the negative x. So let's kind of look at first what rules that we're going to apply to our function. What rules are we going to apply?
A quotient rule and also chain rule.
Quotient rule. So we're going to have a chain rule. Where are we going to have that chain rule?
The e to the negative x.
We're going to have a chain rule here. What other rules do we have to employ?
Product rule.
Product rule. So you look at here, right? You got x ln x. That's going to be a product rule. Okay. Wow, that does not look like a rule that I wrote. Looks like some kind of scribble scratch. Okay. All right. So now we figured out all the rules that we're going to use. Now it's time to put it into practice. This is kind of the point where you want to be organized. Like be organized with this. Not only because it helps you solve the problem, but it also helps who's grading it. This doesn't mean that you have to have, perfect handwriting. It just means that you have to make sure that your stuff's in somewhat of an order that you can use to help you with the situation. So the first thing you can either do both. You can do the top first or the bottom first. I'm going to do the top first just generally because you read things from top to bottom, so it's a little bit easier. So I'm going to mark this with this turquoise color so we can kind of keep focus there, and then mark this with the purple color. All right, so we kind of keep track of what we've got. Okay, hopefully it makes sense. Feel free to chime in if you have any questions along the way. XLN, so we're going to compute that derivative first, okay? So, because the derivative is the product rule of x times ln of x. So the first thing you want to figure out is what your derivatives are. Because the product rule is the derivative of the first function times the second function plus the derivative of the second function times the first function. So you want to have the functions, right? So you've got x ln of x, you got ln of x, and you got the derivatives. So derivatives. Okay. What's the derivative of x here?
1.
That's just 1. And ln of x is what?
1 over x.
1 over x. Nice. Let's put that together. Okay. So we've got first function, right? Derivative of the first function is 1. Let me keep that in the color that I said I was going to keep it in so I can stay organized. So we got 1 times the second function, ln x, plus the derivative of the second function times the first function. So you've got, that derivative is going to be ln of x plus what? Plus 1. Okay. That makes sense? Okay. Let's keep it moving. So we've got the second one. Now you've got the second function. So that derivative is going to be, let me scroll down so that we have some more room. That second function's derivative is going to be, let's see, so we have e to the x plus e to the negative x. So that's just, we're just going to take a derivative from left to right. There's no product rule or quotient rule right here. We just got, something plus another something. So that means the derivative of the first one, then we could do the second one. So let's do that derivative. D over dx. That's going to equal what? What's the derivative of e to the x?
E to the x.
Nice. Okay. I'd like to hear multiple voices on that. It's good to have e to the x. Okay. And then plus, okay, sorry. Well, it's not really a plus here because you got a chain rule, right? The second one is e to the negative x. So that's e to the negative x, right? So we're going to have that e to the negative x there times what?
-1.
-1, right? Because -1 is the derivative of negative x. So we could just have a negative there. Okay. Are we done?
No.
No, not at all. We're not done. So we got more. Okay. So remember that this whole thing is a fraction. So this entire thing is going to be a quotient rule. So we took care, look at all the rules that we've got that we took care of. So we took care of the product rule, we took care of the chain rule, but we still got one more rule left. That's why it's nice to look at a problem beforehand and see, okay, these are the rules that we're going to have. These are the rules that we're going to put into place. So we still got one left. That's the quotient rule. So that's kind of helps you check to make sure that you follow the right steps, if that makes sense. Hopefully, now that you've got your exams online, it's easier to, you have more time to be more methodical with your process. You don't feel like you have to rush. That's like there's a ticking time bomb or something like that. Okay. So let's put together the quotient rule. What is the quotient rule? Let's start there. Quotient rule. The quotient rule. So the quotient rule, let me get a different color for this. Let's get that here. So the quotient rule is going to be the derivative of the first function. So it's like the product rule, okay? So I'm going to do the first derivative times the second function. Okay, this is all in terms of functions. Minus the second prime times the first function divided by the second function squared. So it's a good thing that we computed all of our derivatives first. That now we could just, we don't have to do any more derivatives. We could just plug in all the stuff we have. So we can kind of identify everything literally right now. Okay. What's the first function? The first function is the function that's on top. So that would be this. X, ln x is going to be the first function. So that's going to be the top function. So that's the same thing as the first. And let me rewrite all that stuff on the bottom. Well, y'all, if y'all follow, y'all can kind of finish it out. Let me kind of rewrite this because this is not the not the best way to write it. Yeah. Okay, let me kind of rework it here. Anyway, let me just rewrite it because it's not working. So top times the bottom. This is actually the right way to do it. Bottom minus the bottom prime times top divided by the bottom squared. That's the more correct way to do it. So you can kind of disregard this junk. I mean, it's not wrong, but it's not the easiest way to think about it. Okay, so now we can go back to identifying our stuff. Unless you kind of may have already beaten me to the end of it. This is the top function. This is the bottom function. So, and those are the derivatives. So we can just plug it in. So what do we plug in first? Top function derivative, we figured that to be, what do we figure that to be? ln of x plus 1, is that correct?
Yeah.
Great. And then the bottom was e to the x plus e to the negative x. Okay, minus, let's create some more room. Then we've got what? The bottom prime, which is the same thing as the function itself, just that instead of the plus sign, you have a negative sign now. And the top is x ln x all over e to the x plus e to the negative x 2. All right. That was quite longer, probably due to some technical difficulties, but we did it. Yay. Okay. Any questions before we
simplify that?
you want to, I mean, I guess we can probably simplify that. I mean, personally, I don't really care about that, but we can. Like, you could probably simplify that. If it helped, I would probably simplify it by separating it first. So this is kind of how I would simplify it. So you'd have ln of x plus 1. This is not going to be zoom in for this. This is not exactly what I had intended here. Yeah, I missed my whiteboard. Okay. Have that over. I would first cross out because you have an e to the x plus e to the negative x squared on the bottom. So I would probably cancel out that on the top and bottom first. So I would cancel that out, and then I still have my, yeah. And you can, actually, yeah, I think that's it. That's pretty much it. Your e to the x minus e to the negative x. Yeah, that's probably as best as you can do, I think, given the circumstances. Any other questions? All right. So we're going to do one more derivative problem, but it's not going to be a lot easier. I think you want to go easy to hard problems, and then you kind of want to let them end on a nice, solid W. So, okay. Any more questions before we keep this show on the road? Okay. So that's the problem. Okay. Let's so we got another problem here that we're gonna do. It's actually one from the practice. Not too bad. So it basically tells you that if f of x, the hell? Zoom the fuck in. There we go. They're not like that, but okay, that's better. All right. Sorry about that. F of x is equal to cosine of x. And they want to know what the 107th derivative is. That is. Okay, what is that? So let's kind of think of I'm gonna give you guys actually, let's talk about it together, because this is I picked this problem out because it's a thought process problem. So it's not there's a chat. Sorry, guys. Would he want it simplified? Would he want it simplified on the test, or does he not care? Dr. Joyce is a nice guy. He's my linear algebra teacher, actually. He's a nice guy. So I would ask him, I feel like they would probably be flexible on the simplifications, unless if it's obvious to simplify, do it. But I feel like if it's very tedious, don't worry too much about it, but I would definitely ask him. Okay. Anybody have an idea what the 107th derivative is? So the way you want to think about this kind of problem is you want to think about, first of all, what the derivative is, right? And the great thing is that if you ever have a problem where they want you to think of a pattern, or what's the future value of this? I want to know the 12th derivative or the 37th derivative, or whatever fun number you want to think of. Okay, you're obviously not going to compute this thing 107 times. Not only would that be silly, but that would not be good for your test, because they're not going to give you all that time in the world to do it. The best way to think about it, the best way to approach something like this is to compute the first few derivatives, see what kind of pattern you might get. So let's first do the derivative of cosine of x. And what do we get from that? So let's think about the first derivative. What's that?
Negative sine x.
Station, nice. So that's negative sine x. Okay. What about the second derivative? What about the second derivative?
Would it be negative cosine x?
Negative cosine, right? Because it's a derivative of sine, which is cosine. Then it's negative of that because you're doing negative sine. Okay. What about the third derivative?
Sine of x.
Sine of x. Nice. Okay. So if this third derivative is sine of x, what is the fourth derivative going to be?
Cosine of x.
Cosine. Okay. And I think that's enough because then we're just going to become redundant. But has anybody seen a pattern here?
Mhm.
Yeah.
Negative sign, negative cosine, sine, cosine.
Okay. So, and maybe we should do the fifth derivative. So that will complete the arc. The fifth derivative is the same as the first one. So we just start it over again. Okay. So you computed five derivatives. Okay. And you're seeing that it takes you 4 derivatives to get what you had at the beginning. So at the beginning, right, you had cosine of x, and to get cosine of x again, okay, you would have to take the derivative 4 times. Does that make sense? Took you 4 times to get, it's almost like a circle. So it took 4 times for that to happen. So how would we use that information to figure out what the 107th derivative is? If it takes you 4 times, okay, so if it takes you 4 derivatives to come full circle. So what does that say about the 107th derivative?
You should divide it by 4 to figure out what the remainder is.
Okay, perfect. So we're going to divide it by 4. What do you get from that?
26
Yeah.
with a remainder of 3.
Okay, so 107 divided by 4. Okay. All right, it's 26, and then you have remainder 3. Okay, so remember, I mean, you don't need a calculator to figure that out because 25 times 4 quarters is equal to $1. So 25 times 4 is 100. And then from there, you've got 104, so that would be 26, right? And then you got 3 left. So it takes it till you're going full circle, and you got 3. So what does the 3 mean?
If you land on sine x,
Yeah, so you're gonna take 3 more derivatives, right? So you had 26 full circles now. So that's 26 full circles. And then you have 3 more derivatives. So 3 more derivatives. And so the third derivative, that remember when we took the third derivative, what was the answer to the third derivative?
Sine x.
Sine x.
Sine x.
Yeah, so that's the answer. There you go. So that's how you kind of figure out all this little pattern stuff. So that's the answer. All right. Any questions about that? Okay. So that's our derivative, kind of a little derivative review. I know that was kind of a lot, but it is important to know kind of all these things for derivation. So I'm going to leave it up to you guys we're going to cover next. What do you guys want to talk about next?
Can we go over number 14 on the practice exam, like the last multiple choice?
Fun. So that's going to be, we're going to talk about, okay, word problems. Oh, great. You know, me and word problems have not a very good history, but I can definitely do these. So don't worry about that. Okay, so, all right. So we're going to talk about this. Give you guys like a 3-minute break because that's a lot of math for an hour. So we're going to chill for like 3 minutes. Then I'm going to come back and start solving some of these problems. What's really important, though, is don't fall into the danger of taking practice tests and then only kind of focusing on those problems. You want to figure out if you get something wrong on a practice test, or even if you get something right, figure out what concepts they were testing you in that problem and then go work on those. So if you get a practice problem wrong, especially on a practice midterm, think of the concepts that they're trying to test you on and then go back and review those. So I'm gonna chill for like 3 minutes, then we'll be back. All right, it's time for more math. So number 14, let's go tackle that one. Let me share my screen. All right. So here we have this problem here, 14. So it gives us a function that models the length of a day in hours, okay? Sunrise and sunset. Okay. In Japan, T is the day in the year after the spring equinox on March 21st. Based on this model, estimate how much longer the day becomes from March 31st to April 1 in Sapporo. Okay. So how much longer the day becomes from March 31 to April 1? So what kind of things are this? So let's kind of first get our information. Probably a good idea. Let's see if this thing will allow me to insert a screenshot or something like that. Okay, probably not. I think that works with Word or something like that. Anyway, we can probably still get that information. So start here. So number 14. So we got L of T is equal to Why is my screen sharing paused? Resume share. Okay, there we go. Great. Let me share, do a new share on the screen so that we can be on the same. Okay. I think it's, what is it? 3.4?
Yeah.
3.4 sine of I think it's sine over, let's see, sine over 2 pi. Okay. Thank you. 2 pi 365t. That's our equation. Then we kind of want to know. So we're told that T is the day in the year after the spring equinox. Okay. So we'll start off on March. The time intervals kind of starts on March 31st. So not 31st, sorry, March 21st. So days after. All right. Days after March 21st. And then we want to know how much longer the day gets, because the day gets longer as you go past the equinox. So we want to figure out how much longer are we going between March 31 and April. So we're trying to figure out how much. So if this whole equation, okay, if this whole equation is talking about the length of a day in hours, okay, and we want to talk about how much longer a day is, what does that infer?
Well, you're gonna subtract one day length from another day length and then convert it to minutes.
Okay. Right, but that's part of it. So we are going to do that. But if we're going to, so what I want to kind of, my point that I want to get across here is that we're going to be doing a derivative. The reason why we're going to be doing a derivative is because the day is increasing. So your day length is increasing. Okay, and you're trying to track that increase. Okay, so you're trying to track that increase. Not increase, increasing. Okay. So first, let's figure out our information first. What exactly the problem wants to solve. So we want to figure out, we want to estimate how much longer the day becomes from March 31 to April 1. Okay, in Sapporo. So what we're going to do is we're going to do a rate of change. So we're going to have first, okay, you're going to have April 1 information and March 31st information divided by the length of time in between that.
Sorry.
All right, cool. So let's get that information. So April 1 is how many days from March 31st? That is going to be 11 days. Right? So 11 days, April 1, and 10 days is, this is April 1, March 31. All right, great. So go back to our equation. And then now, I think I'll let you guys use calculators on the exam. I mean, you might as well. I mean, you're taking it at home, so you might as well use the calculator. So I have a calculator here. We're gonna first try this approach. So Yume's approach that she proposed was that we're gonna plug in the days, and then subtract them, and see how much longer your day ends up being. So if you try that and you plug it in, so let's try that now. So you got 2 pi, you're gonna have 2 pi times 11, right? Because that's 11 days is April 1. So April 1 is more days, so you gotta start there. 2 pi times 11 divided by 365, and then you're gonna take the sine of that, okay, times 3.4, okay, and then that's gonna be, I think, let's see. Well, actually, yeah. Is T in minutes or T is the day? Okay, T is the day. Okay, so not in minutes. So it's gonna be plus 12 is gonna be, let's see. So April 1, it's gonna be about 12.01. Is that, y'all get that?
Mhm.
Okay, so let's do that. So something like that. March 31st is the same calculation. You're just doing 10 instead of 11. $3.4 plus 12. So you got about the same. You get about the same value, practically. In, what is this? The length of a day in hours. So this is pretty much the
I
length of.
didn't get those values for.
Excuse me?
I didn't get. Do you use Is it like a radians versus degree mode thing? I didn't get the.
What is your
those
calculator?
numbers.
Is your calculator in radians or calculator in degrees?
Radians.
I think it's okay. So I think mine's also, I believe. Let me check my mode. But makes sense that it's 12 hours though.
Yeah.
What numbers are you getting?
I got 12.64 and 12.58 for.
Okay, then you probably have that's probably what sounds more correct. Considering that yours is in radians. Yeah, mine's in degrees. So let me, yeah, your thing should always be in radians, at least as a default. Okay, 12.64, 12.58.
Mm-hmm.
Okay, that's like a point. That's a 0.06 difference. So 0.06 times 60 is 36 minutes. As you can see, 36 minutes is not an option.
You need
So-
to also multiply it by 24.
No, 0.06 times 60 is 3.6.
3.6, sorry, yeah, 0.06. I put 0.6. Okay, 3.6. So has B as 3.5. Okay. So are these like rounded estimates, you may?
Well, for t equals 10, I got like 12.582, and then for t equals 11, I got like 12.639. But yeah.
Okay,
I got the same thing.
nice. Okay, that seems That seems like B is the answer. So hopefully Stacia, that answers your question. But as with all of these, I will double check with Dr. Joyce and get back to y'all before y'all exam. Y'all have like all day money to take this exam, right? Or is it like a specific time of the day?
We have all day, like from midnight to midnight.
All right.
You only have 2 hours. One.
2 hours.
So you have 2 hours once you agree to take it.
Yeah.
All right.
Yes.
Okay. So that's 14. I'll get back to y'all hopefully by Sunday on the answer to this. I think it's B. Can't be. Don't. It would be wild for the answer to be anything higher than C. That would be pretty wild. Days don't increase that fast. Okay. So let's kind of figure out what else y'all want to go over. So in terms of like, I know you may have certain problems you want to talk about. So what other problems you might want to talk about?
Could we go over 5? Or no, never mind. Not that one. 11 on the practice exam.
Oh, fun. Okay. So let's talk about it first. What's the instantaneous rate of change? What is that? What clue does that give you?
You need to find the slope, which is the derivative.
Correct. The derivative. Okay. So first you need to take the derivative. So,
Yeah.
so
When
take
you
the,
plug the t, I guess I was just confused. Like, would you plug the 10 in for t before you take the derivative of,
No.
or after?
after.
After.
See, okay. I always recommend that you take your derivative after you thought you take the derivative. You plug in your constants or your numbers after you're taking the derivative. That way you could do it all at one time. If you plug it in before, you could get confused. Here, okay. K is a constant. Okay. K is a constant. Is T a constant or is T a variable?
T is a variable.
T is a variable, right. So the mistake that you could make is if you plugged in T immediately is that you may think that T is a constant. Not that you thought that, but that's just a general kind of thought that you might have thought, hey, T is a constant, so I'm going to, you think that that's a constant and solve it that way, which would be wrong. So do you want me to take this derivative or do you think you got it from here?
Could we take it just because, like, I got, like, the derivative that I got was, like, kt plus 1 minus k times t all over kt plus 1 squared. But that wasn't an option, I didn't think, in the multiple choice.
All right, let's take the derivative then. So they want the derivative, they want the instantaneous rate of change of the concentration. And the concentration is measured by KT over KT plus 1. Is that correct?
Yeah.
Cool. All right. Like I said before, you want to keep your stuff organized. This is like the other derivative that we dealt with earlier where you had the quotient rule. You want to identify the rules that you are going to have first. Okay, so let's do that. So we've got fraction line, so that means we're going to have a quotient rule. Quotient rule. That's about it. That's about it. That's really the only rule you're going to use. So given that in mind, okay, because you have the quotient rule, you know that the derivative of the bottom is going to be what?
KT plus 1 squared.
Squared, right. Nice. So it's going to be KT plus 1 squared. So any answer don't have that, something like that along those lines is not going to be correct. Okay. So
yeah.
A, nope. B, no. Well, unless you cross it now, but I doubt you're going to R. A, B, and E look out right now. We're not going to rule anything out right now, but they look like they're probably not going to be the answer. Okay. But let's keep it going. So you got the derivative of So let's first get our derivative. So that derivative is what?
Would it just be t?
It's just t, because k is a constant. Okay. What else do we have? So what's the derivative of the bottom?
Would that also just be t?
That is also t.
Okay.
Okay. So now we're going to have the derivative of the top times the derivative of the bottom, which is derivative of the top times the bottom. Sorry. So you're going to have t times k t plus 1 minus t times kt.
Okay.
That's hopefully this makes more sense as
Yeah,
they've been going along.
Thought that you had to do like, I guess I was like taking like derivatives and using k as something. I don't really know what I was
Okay. Well, that's okay. We have it all figured out now. So,
Yeah.
All right. So this is your, I guess you could factor out a t. So you could have t factored out and you have kt plus 1 minus kt. So over kt plus 1 squared. This is probably when you probably should simplify. Then you're kind of left with t is going to be on the top. So it's just going to be t. Because these k's, these guys are going to cancel. You have t times 1, which is just t. And kt. This is why I said numbers at the end, because that makes it a lot easier to finish it off. So plug in 10, because it's 10 seconds. Now you've got 10 over, so it's going to be 10k. So you're going to have 10k plus 1 squared. Is that an option?
I'll pull up right now.
Yeah, it's
Yeah.
is it? Nah. I don't
Or-
think it. No, it don't look like it is.
Wait, no.
Don't okay, what are we missing here?
Well, like, isn't the derivative of kt, wouldn't that just be k, not t? Because if it's like
Yeah,
constant, it's like 2t, so it'd just be 2.
yeah, you're
Or
right. You're right. You're right. You're right. You're right, Stacia. You're right. You're right. That's where we made our mistake. Yeah, it's not t.
And then
It's
I thought the answer was d.
wait. It's just. Excuse me.
I got the answer was d, so it'd just be k instead of t on the top with the same denominator.
Okay. Yeah, that looks to be right. Right. Okay. Cool. So I was good to have multiple people on this. Good job, Station. Okay. Yeah. So it's not t. It's so I even got confused about what I said. You shouldn't be confused about. That's why you don't want to think about numbers at the beginning. So it's k. Is k, not t. So we're going to replace all these with k.
Oh, the derivative is k?
Yeah, because k is the constant. So like think about it this way, right? If you just wrote in like the derivative, like I don't know,
Oh, like 2x?
like 2x or like 4x, right? The derivative of that is just gonna be 4. So that's where it kind of, there we go. So they got me on this one. So maybe y'all should be teaching this class. Okay. So there we go. So that makes it a lot simpler for us. It's gonna be k. I think that's an answer. So that's D. So Stacia's right. All right. So that's kind of just a derivative thing. D is the answer. D for derivative, I guess. All right. What else y'all got?
I was like confused with number 3. I don't know if anyone else was, but
Oh, related rates.
yeah.
Okay, how do y'all feel about that? That's some historically in calc classes, people have felt kind of uneasy about that. Maybe y'all a lot smarter than them, so maybe y'all don't. But that's something that y'all want to talk about. Related rates. So that's something that, because that means that you gotta know what implicit differentiation is. So y'all required to know implicit differentiation, right? Are y'all? Okay. So y'all, okay. Because if y'all aren't required to know implicit differentiation, the related rates wouldn't make any sense, but related rates is on your practice midterm. So
Current differential, is that like when there's different, like you have to do like dx, or there's like x's and y's and you have to do like dy?
yeah, it's like that.
Yeah, we have to do that.
Okay, so if you gotta do that, then that means you gotta do implicit differentiation. So first we're gonna do a little implicit differentiation recap. So let's kind of first map out the session, right? Let's kind of first map out what else is left. So what we have left to cover. I mean, I have stuff here. I always have notes of myself, but problems do you want to do? But obviously this is y'all's session, so it's important that we get y'all's feedback on what we need to cover. So related rates is one of them. So that's just something that we've been asked to cover. What other things do you guys want to talk about before this session is over? This session is being recorded. Yes.
Can we do linear approximation? I think 2 has that, and 8.
Okay, so linear approximation. That's actually easier, so I want to jot that one first. All right, anything else that anybody wants to cover?
I don't think we're supposed to know implicit differentiation because he said we're not doing 3.5 from the textbook. And that's what that is.
Okay.
But I don't know.
So it seems to me that Dr. Joyce is not going to ask you a direct implicit differentiation problem, but that you are going to have to do related rates, and related rates requires knowledge of implicit differentiation. Unless you guys were taught a way that you didn't have to use implicit differentiation. I was taught related rates using implicit differentiation on how to do that.
Yeah.
Has anybody tried number 3? Because I did number 3 like 10 minutes before the session. So has anyone tried 3?
I mean, I tried it, but
Did you use implicit differentiation?
yeah, I did like when I got like a squared plus b squared equals c squared, I did like 2a dA dt plus 2b db dt.
Okay. And where did you run into trouble?
I guess I just like don't really understand what variable I was looking for, and then
Okay.
I got confused because it was only like the bird was flying like 500 meters per minute. And so I didn't know if I like put that rate into both of the dA dt and the dB dt, or like I didn't know if it was like a constant rate. I don't know. I just get confused with like the inputting of stuff.
Okay. So you guys want to talk? So we have related rates, linear approximation, and is that anything else you guys want to cover, or is this kind of just more of let's see how the session rides out? Because we got, if do y'all feel comfortable with logarithmic derivatives in case he throws them out there? But probably don't. Maybe not. You don't have to know that since y'all don't have to know implicit differentiation. I don't know. Y'all know what y'all got to cover. Okay. Because Dr. George told me 3.1 through 3.10. So I'm prepared to talk about all that stuff. It's just that I want to make sure that, okay, these are the people who chose to come. So let's get the max that we can for them. Okay. So while we're at this, let's do some related rates. Let's do that problem. And then we might do another one because related rates is, you don't want to keep that. Let me first share my screen with y'all. Okay. We are going to share screen. All right. Y'all can see my screen, right?
Yeah.
Thanks. All right. So we're going to do the problem from practice midterm. Cool. So let's talk about what the problem is telling us. So there's any, in fact, based on you, because you guys have heard me read problems and kind of get information from that. So let's do it from y'all's perspective. What does the problem, what are you seeing from the problem? What is the problem? What kind of information is the problem telling you?
Well, you know that like I drew like a little picture with like a hunter and then a bird above him, and you know that that's 80 meters.
So you got a hunter and you got a, let's draw a hunter. I don't know how we're going to do that. Maybe I can draw like Daniel Boone or something like that. Like a rugged hunter with like the, you know, those little like caps or something like that. Okay. All right, hunter and a bird. Forgot we're going to draw this bird without offending anybody or offending birds, since those guys are powerful creatures. All right. That's a bird. All right. Looks weird, but it is a bird. So once we have that, you said that was 80 meters above the hunter.
Yeah.
Okay, what else?
And then we're trying to find like the rate that of distance that increases between the hunter and the bird when the bird is 100 meters away.
So when the bird is 100 meters away. So at our time point, we're looking at when the bird is 100. No, that's a wildly inaccurate line. Okay, 100 meters away. That's kind of when we're looking at the whole thing. And you said the bird is flying 500 meters per minute horizontally.
Yeah.
So that way.
Or I'd say at least that's like when the bird was 80 meters above the hunter.
Okay,
so is
cool.
it a constant rate?
That is, let's see. So that's constant at that point, yes.
Okay.
So it's a constant at that point, but the speed is changing. So we're gonna figure that the idea is to find, okay, so we're gonna assume that this thing is constant. But the idea, what are they asking you? Let's kind of figure that out. What are they asking you?
Oh no. Let's see.
Aren't they asking like dz over dt? So like the hypotenuse rate, basically, I think.
Okay. Julie, that is correct. That's what they're asking. So nice. That's what they're asking. That's exactly right. That's what they're asking. Sorry. So they're asking what in terms of the, I want to say the distance between the bird and the hunter. Okay. They're asking what distance are we increasing? Okay. So, and Julia mentioned the hypotenuse. She mentioned the hypotenuse. So the hypotenuse is definitely a way, definitely one of the keys that we're going to use to solve this problem. So let's try to unlock that key. I like black, so let's keep it black for now. Well, this looks weird now. Anyway. So hypotenuse is another way of saying, oh, we're going to be dealing with a triangle. So let's kind of make our triangle. So we're going to make a model triangle here. What? And we're going to label all the information that we have. So we now have our information triangle. And we want to know the hypotenuse, the distance of the hypotenuse in terms of how fast is the distance increasing. So how fast is the hypotenuse increasing between the bird and the hunter? But in order to get all that information, we need to figure out what kind of equation we're going to use in order to get that hypotenuse. And what equation would that be?
The Pythagorean theorem.
The Pythagorean theorem. Cool. So we got a squared plus b squared equals c. C is the hypotenuse. I'm going to use x, y, and z, not a, b, c, because that's what I wrote on my paper, and that's just kind of how you're thinking about it in math terms. But yes, they're the same thing. So I'm just going to draw an arrow. Okay. So we're going to label it on a triangle. X, Y, Z. Great. What information do we have? And I'm going to redraw this triangle over here so we have some more room. Let's fill in with our information. All right. What information do we have?
We have x and y.
So we have, yeah. So what's x? What's x?
80 or 100.
X is 100. Y is, that one's 80.
80.
Okay, so you could find out what z is. The z is when you've got 80 and 100. Okay, but those numbers. So, but there's the budget changing factors. So the z, you could solve for z now, but it wouldn't be the z as the distance is increasing. It would just be the z distance when you have 180 as your other two values. So because something is changing, that implies that we're going to be talking about a derivative. Hopefully we have hammered that into our heads by now. Derivative, changing, derivatives involved. What's the derivative of this function? First of all, what are we taking the derivative with respect to?
Time.
Nice. So we're talking about derivative with respect to time. So you're going to do implicit differentiation with respect to time. This is how it's done. So I'm going to do it directly just because I'm not sure exactly how grilled you may be in implicit differentiation, but in case you aren't, follow along. Take derivative from left to right. X squared derivative, you know what that is. That's going to be, so first you take the derivative with respect to the variable itself. That's how implicit differentiation works. So we talk about implicit differentiation, okay? Implicit differentiation, okay? You're going to take the derivative with respect to itself, and then you're going to multiply that by the derivative with respect to time. In this case, another input differentiation problem is going to be with respect to x, but in this case, it's with respect to time because you have something flying at meters per minute. Okay, first derivative is going to be 2x times derivative of x with respect to time, which is going to be dx over dt, plus 2y dy over dt. Okay, and that is going to end with the derivative with respect to, to z times the derivative with respect to z. We'll see, we'll check the time. That makes sense, everybody?
Yeah.
Okay. That sounds okay. Everyone seems to be okay. All right. Let's keep it going. So, what's next for us? Now it's time to figure out. So, what we're trying to figure out, we want that. Okay. That's the hypotenuse, because we defined this. We defined the hypotenuse as z. So we want that. So how are we gonna? We need to figure out. Okay, first you want to solve for that. So very algebraically, you can very simply just divide both sides by 2z. It's 2y dy over dt over 2z. So you could probably, like I said, I like to do all my number stuff at the end after I've already figured out, my simplification and everything. So we could probably get rid of these 2's because every term has a 2. So then you're going to be left with dx over dt, x dx over dt plus y dy over z. Okay. Now it's time to plug in our numbers. So what are our numbers? What's x going to be? We already defined that, right? We already defined x as 100. And we defined y as 80. What's dx over dt?
Is that the 500?
That is the 500. Remember, these are all in meters, so let's not forget our units. Meters per minute. Okay. And then what's dy over dt? Ah, 0. There you go. I knew Stacia would come through. 0. It's 0. Okay, and it's 0 because the bird is flying horizontally. So it's not like the bird's coming down or anything like that, or going even higher. It's going 500 meters horizontally. So that's how we know it's only going in the x direction, not going in the y direction. And of course, z, you can solve for z, right? Right. You can solve for z using the Pythagorean theorem. So whatever that is. Your calculator can figure that one out for you. So at the end of the day, you've got, let's see, you've got 100 times 500. So you got 100 times 500 over this hypotenuse value. And I think at the end of that, your calculator can confirm, but you should get a value of, check me on this if my calculator is right, 390.4 meters per minute. I hate related rates, but this is a pretty good way to practice implicit differentiation, and also a good way to read problems and figure out, okay, what information am I extracting? Hell, if I wrote a test, every problem would be a word problem. But good thing I'm not writing tests. Any questions about this process? Does it make sense, this process?
I thought the hypotenuse was 100 meters. Is that not right? Or
That's a good question. It really depends on how the question is phrased and how you understand it. So when it's saying that the bird is flying horizontally at an altitude of 80 meters, that makes sense that you have an altitude that is, altitude is in terms of like height, right? So that's clearly vertically. So that's y. And then of course, the 500, that's going horizontally. And then you want to figure out what rate is the distance from the bird to the hunter increasing when it is 100 meters away from the hunter. So, you could do the same thing normally when they ask questions like that, they're talking about the hypotenuse, which would be z. But you could claim that they're trying to solve this. You could solve this problem with it talking about in the x direction. Your problem with that would be your variables, because the 500 is clearly in the x direction. So, because it's flying horizontally.
No, yeah, but like, wouldn't z be 100?
Well, if z was one, so if z was on 100, then if z is 100, then are we solving for d? Are you saying that we're solving for dx dt? Maybe.
But like, you'd still solve for like dz over dt. But like, if it's like the bird's distance from the hunter,
Okay.
isn't that the hypotenuse?
Yeah, it's the hypotenuse. That's z.
Then like z would be 100 meters.
Okay, so you're saying z would be 100 meters, and then y would be 80, and then you're saying, okay, x would be 60.
Yeah.
Okay. Okay. That's actually a good thought. That is a very good thought, because we can still make our modifications that way. So yes, I'm going to, so alternatively, okay, you could figure it out that way. So you would then rewrite your triangle, right? You would then rewrite your triangle. This would be 100. And this would be 60, and that would be 80. That's just a basic Pythagorean formula. If that was the case, then you're still solving for dz over dt, which then would be, you're still dealing with dz over dt equals x times dx over dt plus y times dy over dt over z. Then that would be 100. You're saying that would be 100. That would be 60. That would be 500. And then that would be 80. That would be 0. Okay.
Yeah.
That's going to be what? 300 then? 300 meters per minute? Anybody else get 300 meters per minute?
Yeah, I did.
Okay. So what I'm going to do, as always, because I could see that that theory. I could see, and yours probably sound more right. Okay. So I'll again ask Joyce and figure out which one of these is correct and let y'all know. But I think this is more so a question about how is this thing phrased, so that's really the question, like how is it phrased, right? Because if you're dealing with the rate at the distance from the hunter to the bird is increasing when it's 100 meters away from the hunter, 100 meters in what direction? Okay, so that is important to know. So I will inquire about that. But thank you guys. You guys are really smart. Y'all are figuring this out. Okay, that's our related rates problem. Any other questions? Other than the linear approximation question that we had, which we can do. All right.
I have a question for number 6.
Oh, is that the exponential growth question?
Yeah, but since it's like half-life, would it be like the two last answer choices that like I'm looking at? I don't know if it'd be negative or positive.
Okay. So you're looking at D and E.
I'm looking at B and D.
B and D. Okay, the last one is B and D. Okay. All right. So, I mean, clearly is one of those two, right? Because you have a 30 milligram sample, and the initial amount of grams you have is 30. So, just based on process of elimination, okay, 30 is going to be the constant. So, for those people, for anybody who may be struggling to follow along with what we're talking about, exponential decay, practice midterm problem. So we're dealing with number 6. All right, so the formula is P of t equals P naught, or the constant, e to the kt. This is the initial amount. So the initial amount is 30. Okay. So D or the D, or it's either D or B or D. Okay. Now, so your main question is about whether or not it's negative or not. Well, let's think about it. Okay, is the constant, what is K? Because the T, we have K and T, right? K and T are a part of the exponent here, right? So what's K? Is K negative or is K positive? What does that imply? What happens if K is negative?
Negative K means decay, right? And then positive K means growth.
Right. So are we decaying or are we growing?
Or decaying.
We're decaying. It's half-life, right? So we're decaying. So based on that, I would figure that the answer is B. But obviously, you want to always check your work. Let's do that. So if we're going to measure that time, we're measuring T's in years. So let me put that note there. That is in years. Obviously, you want to figure out, so we know that that's 30 off the bat, but half-life is half of that, right? That's 15, right? That's half of 30. So half-life, 30. So that's 15, half of 30 is 15. Okay. It goes 30, E, K to the what? 1. So it's, but they already told us what it was, right? 16 years, 1600 years. All right. Time to figure this one out. You can divide on both sides by 30 to get 1/2 K 600. All right. How do we get rid of exponents, guys?
Wait, would you write negative K there or no?
I haven't written any negative yet. But yeah, would I write negative K?
That's what I was confused about.
Okay.
I think we may end up doing that, but let's keep going on this while we are on it. Okay. All right. Because I'm trying to deconstruct the equation from scratch right now. Okay. So if you want to get rid of the exponent, you take the natural log. So that brings to the front. Now you got K, 600K, ln of E, which is 1. That equals ln of 1/2 is a negative number. So this is where the negative will come in. From your property. So that's just a review of a logarithmic property. So if you've got two numbers divided by each other within a natural log, you can split them up into the top number minus the other number, like this. That make sense? natural log of 1 is 0. So your answer is going to be k is equal to natural log of 2 divided by 600, 1600. That is your constant. Now, which one of those matches up with that? That would be B. So that's your answer. That makes sense?
Yeah, I was just unsure where you'd put the negative or like when.
I mean, the negative came organically. It's not a, I mean, from like, I guess you could say, you know, from what we were talking about looking at the problem and trying to figure out what it's saying. It is radioactive decay because of, you mentioned half-life. So that is a decay. So your K constant would be negative, but to prove that, we just constructed the equation from scratch, and it organically was negative. There was no time where you insert the negative on your own. That came organically here, as you can see. All right. So I believe I promised linear approximation. Well, we good on exponential decay before we move on? Okay. So let's get into that. Linear approximation. Linear approximation, I don't think is that bad, but that's kind of, well, is there a specific problem that y'all want to talk about linear approximation, or should I just make one up?
Can we do number 8?
Yeah, we could do 8. That's the, oh, fun. Okay. You know, the key thing is you have to remember with the formula. That's kind of the key thing behind this. What is the formula? So it's going to be, in case you may not remember what the formula is. So L of x, that's the linear approximation function, is equal to the function that you're trying to approximate at a point A, okay, plus the derivative of that point, derivative of that function at that point, and then the value that you're trying to approximate, sorry, minus the x value. Okay? What's our function? Where's the function f gonna be? Okay. So our function is gonna be sine of x, right? That's gonna be our function. It's gonna be sine of x. So let's put that in there. Sine of x. That's gonna be our function. We're trying to approximate at when a is equal to 0. Okay, so it's time to just fill in the blanks. So let's put the function. So we got, this becomes what? Sine of a, right? F of a, sine of a. What's the derivative of sine?
Cosine.
Sine of a. Okay, and then we have x minus a. So x minus a. Good job on the derivative. Cross some stuff out. A is 0, so that's 0. This is 0. And then this part is going to be 0 also. Okay. What's sine of 0? What's cosine of 0?
1.
1. So cosine of 0 is 1. So that must mean that the sine of 0 is
0.
0. Perfect. And of course, this is just x. So your answer is going to be what? 0 plus 1 times x. X. I think that's B on there. So your function is actually sine of 3x. Sorry, not x, but it's still the same thing. You're still going to have 3 times 0 is 0 still. So it's still going to be 0 here. So it doesn't really change anything. Oh, it does change something, actually. Sorry. This derivative is going to change. Yeah, so sine of 3x, sorry, not sine of x. So your derivative is going to be 3 times cosine times 3a, right? Because you're going to the derivative of that is going to be sine, derivative is cosine of the input. So you got cosine of 3a times 3 because of the chain rule. This is going to be not 1, but 3. Then you have 0 plus 3 times x, which is 3x. So that's actually the correct answer. So it's not B. It's going to be, what the hell? I did not intend that. What the hell? Okay. Malfunction. Not B, but C. Okay. Any other questions? All right. So that's pretty much, seems like y'all don't have any more questions. So that seems like what we've got for today. Of course, y'all are always free to reach out in case y'all have any other questions on this. I'll stay for a few minutes after in case anybody has any like personal questions they want to ask me about this. But other than that, that's a wrap. Good luck on y'all exam. Hopefully we'll see y'all in the future after the exam's over.
Thank you.
No problem. That's a wrap.